Kanvarti with Avilash Sarkar. And now we are moving on the part of the fluid dynamics, that is the continuity of equation of continuity. Basically, this says the mass flow rate is same, and from there the volume flow rate is same. On that we did some example. Now I will move on to third example of that. Then I will move the further theory. The third example is that it says the cylinder tube of a tube of a spray foam has a radius R, capital R, one end of which has in fine holes each of radius small r. If speed of liquid is v, and speed of ejection is how much? Okay, so let me draw it for you. This is a cylinder. Okay, this is a cylinder. So one side, this is a cylinder pump basically. One side is a radius. This, if I say this, having radius of capital R, and there are small fine holes. Okay, small fine holes are there on the other side, and each of radius R. Okay, and number is count is equal to n. So as this is spraying, we can take this is a steady flow state is happening there, and we'll use the equation of continuity. By using the equation of continuity, there's flow in, this is the velocity v, and through each hole, what is the speed of ejection is how much? Ejection means through each hole what will be the velocity. So the cross section of this is say one position, this is two position. In two position there are n numbers of hole. So a1 v1 as first position is equal to a2 v2 the second position, but a2 v2 here will be uniform or equal in all, so that has to be multiplied of n number of what I said, what is in, or rather we'll go with the basic one, flow in equal to sum of flow out. This will be the basic equation. By that there will be no chance of mistake. So basic flow in is there is 1. So 1, that means A1 V1. Summation of that means n is equal to starting from 1 to n. So that is, I will take n numbers, but those are of identical. So there is no problem of multiplying n identical mass, because if we add 1 plus 1 plus 1, that and multiplying with n is equal to 1, if it is number is n, so that will give you the same result. So n is equal to into a1, a2 and v2. This will be the case. So if I do a1 of this is equal to pi by 4 or pi r square. This is not d, this is r. Sorry, I missed it. This r, that means half. So pi r square into velocity v is given, and there is n into a2 is equal to pi r square, small r square, into the velocity that you need, v2, let's say. So from there v2 will be equal to pi will cancel down, r square divided by n r square will be your velocity. Okay, through each hole. Okay, so fine. Here I will end up this equation of continuity and related problem. Now the new subject that will start is Bernoulli's theorem. Okay, so this is Bernoulli's theory. So what is this theory all about? If I say there is a conduit or a flow path of such kind, this is the end position and this is also end position, and at particular time the liquid through passing through this is this way it is happening. Here the inlet velocity is v1 and outlet at this point, at point 1, point 2, velocity and cross section is a, cross section is a2, this is a1, like that. Now what Bernoulli's theory is saying is in case of ideal fluid in steady state flow, the energy at any point of flow is conserved. Okay, so let me remind you again, what is ideal fluid? Ideal fluid, it is incompressible, irrotational, ideal fluid is incompressible, irrotational. Incompressible, that means no change in density. Okay, so this is the ideal fluid case. So, and irrotational, this is the other case. So in such cases, the fluid in a steady state flow, energy at any point of the flow is conserved. So what are the energy that if I want to bring at point 1, what are those energy? Let's say there is a pressure is P1, there is pressure P2. Now in a duct the flow is established that needs some force to flow. That means if the and velocity was okay, Now, if the liquid is, if the fluid is flowing through any duct or any path, that means from the start of the flow towards the end of the flow, there must be some force is acting. Okay, so that force is being counted, as you will see, uh, in case of a static fluid. In case of static fluid, the pressure here and the pressure here having difference, and this pressure here is causing due to the this fluid column. Okay, the pressure is P0, here is P0 plus H rho G. Okay, so now the pressure here with respect to somewhere from where the fluid is coming, let's say this pressure can also be created by a machine. It can be thrust into that conduit, and so that this pressure here it is more, and due to that there is a possibility of flow. Otherwise, if there is no difference in between the flow, as I seen for YouTube problem, till the head is same in both, even though the cross section is high, there is no flow. So to only to get flow into the arm, or there needs some head, I means the pressure energy due to the height. So we can assume if it is flowing either through a machine or by head, it is by height of the fluid it is flowing. So that means there is a naturally one pressure, that is pressure P, one is acting, that pressure plus this is the pressure energy. Okay, how come it is pressure energy? Oh, one thing is that in case of fluid, the energy per unit volume, you have to admit that per unit volume will come. So pressure here per unit volume is P1. Okay, so pressure here per unit volume, if I multiply with the volume, it will get converted into the energy unit. So the pressure into the volume, so per unit volume the pressure is P1, and that of the energy, that the kinetic energy, there is velocity, so what I will get, the kinetic energy half m v square, v1 square. This is mass flow rate, this is mass into, this will be the energy for any segment at one. If I say the mass is flowing through that is m per unit time, so that is equal to mv square is the energy. But what we say, by volume, per unit volume, so I have to divide by volume, so this will be the energy per unit volume, that is the kinetic energy. The equation will be the pressure energy plus kinetic energy plus potential energy. So this at point 1 per volume at 1 equals to, so same pressure energy plus kinetic energy plus potential energy per volume at 2. This will be our energy conservation equation. Energy per unit volume at 1, energy per unit volume at 2. So in case of ideal fluid, in steady state, the flow energy per unit volume at any point of flow is conserved, that will not vary. So from there we can say what is pressure energy, this is P1 per unit volume pressure at here. Okay, plus half mv square, that is the kinetic energy, divided by the volume v, and that of potential energies, what is that, h mgh, sorry, mgh H is potential energy divided by volume. Okay, this could be same. Now if I take this is H1. Now H1 height from where we have take, we will take. So in case of flow, for each place the mass, we can think of that the mass is concentrated at its center. This means a complete mass can be assumed to be there concentrated at one point according to the shape of the flow path. So that means if I assume that the center of mass is moving as the flow is moving, taking the same path, if I add all the center of mass of the all segment, which this segment, this segment, if I add all the center of mass and you can assume a path through this, so this path with a reference, let's say this, I have to take a reference from where I can take height. This height is h2, this height is h1, this is center of mass of height, this is the center of mass of the flow path of the flow volume or mass of each segment. If I add all the center of masses, dividing it into several, the more smaller segment we can get, will get more finer path. So if I add this will move through a path, and if I take height from this reference point, this is our reference point, reference plane or point or line or whatever you say, from there I am taking a height of the particular point at which I have to consider the energy. So that height is the height of that portion's center of mass. So center of mass here is there, so from there I will take. Okay, so now the pressure energy at here is P1 plus the kinetic energy is half m V1 square divided by the volume. Okay, volume plus kinetic potential energy mgh upon volume, and this is at 1. So this height is denoted by h1. So there another, and point 2, the pressure is P2 plus half m V2 square by volume. Okay, plus this volume will be accordingly to this part. So you can take the volume. This is I have to denote with capital V. This is small v to distinguish between the volume and the velocity. This is V1 velocity, small capital V. This is V1. This is this. Then mass flow rate here is it is same. So that volume has to be accordingly same. The density is not changing. The volume is V1, or you can take V, the volume, and here it is mgh2 divided by the volume. Okay, because this is incompressible ideal fluid, so the mass, if it is same for a particular point, so the volume also will not change as density. So I am taking all the volume same. So it will convert into the pressure energy P plus m by v. This part is your density. So half into density v1 square plus this again the density rho gh1 is equal to p2 plus this again rho half rho v2 square plus rho gh2. So this is your equation of energy conservation according to the Bernoulli's theorem. So when an ideal fluid flowing and the energy is conserved at any point of time, from there we can say if I take the point 1 and 2, that energy is conserved. So from there we can conclude, as it is said, instead of writing all this, the basic equation will be pressure energy plus your kinetic energy per unit volume plus your potential energy is constant. So this is your ultimate Bernoulli equation. So for any value of pressure energy and kinetic energy and potential energy, the sum of the energies are constants. Okay. So now we'll take the case of one by one. Take the case one by one. When now this can also be converted into head equation. What is the head? Actually, the pressure head or kinetic head or the potential head. This head can be defined by the if I divide it by rho g, because I have to bring here head, means this potential energy will be represented as head. If I say the potential head is 10 meter, that means you have to understand that 10 meter has to be multiplied with this to get the potential energy at that point. Okay, similarly this will be converted according to this. So if I divide it rho g plus half rho g, rho will cancel out, v square by g plus h, this will is equal to the head equation. Head, that means the energy head. Now if I have asked to represent the energy equation in terms of head, so this will every term will get in head, and the equation will be, as this is in meter, this also to be in meter, this also to be in meter. Means if I talk about the SI units, so head, if it is said is pressure is this much meter, velocity is this much meter, this is this much meter, so this is total head. Okay, now this has to be multiplied with rho and g in SI to get the complete energy in joule or something like that. Okay, so this will be, you have to understand that from this equation. So this is pressure energy, this is the energy equation of Bernoulli's equation, this is head equation of Bernoulli's equation. Okay, so now we'll talk about something more on this. The condition is, if the fluid is in rest. So now if the fluid, now we are moving into dynamics when the fluid is started moving. Now we are saying if the fluid is rest, whether this condition is same as the fluid fluid statistics. Let's see. Now if I put this condition, this equation must convert into the equation of fluid statistics. So when it's rest, that means velocity is equal to 0. Putting velocity is equal to 0, but I get pressure energy plus rho gh is equal to a constant. Sorry. So in case there is no velocity, your pressure energy and rho gh, what is that? If I can remember, in a container filled with some fluid, the pressure energy at here is P atmospheric and pressure energy here is how much? If I say this is P1, so P1 is equal to the atmospheric pressure, that means P0 plus the height, if it is h rho g. Now see, this is matching. So pressure energy is what? P0 plus h rho g is constant. That means at any point of time, it's any point here, if the height difference is same, so this is equal to the P pressure energy plus P is atmospheric pressure. This is due to the height it is deviating. So ultimately the P at any point it is same. So that pressure energy, if it is not flowing, the pressure energy at any point of is at the bottom is same, or any elevation if I take in any cross section, that will be same. That will depend on the height only. So this is constant. This is just as we study in fluid statistics is the condition. So fluid at rest, it can be fetched from this Bernoulli's equation. Okay. Now the second condition, if instead of getting different height, if I say the fluid is flowing through a horizontal pipe. Okay. Now here from this reference, the center of mass of height will be same, h will be same. So there is no height difference between this equation. There is no, because whatever, if it is constant, if I take 0.1, 0.2, earlier equation is the P1, here P1 plus half rho V1 square plus 8 rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. This could be the equation. Now H1 and H2. This is your H1. This is your H2. Now these are in same elevation. So if it is in same elevation, this will be cancelled out. So remaining is P1 plus, rather P, you can say the universal equation will be half rho velocity square, that will be a constant, isn't it? So for the pressure energy and the kinetic energy per unit volume will be constant. So in case of same elevation, the fluid is flowing, this could be another possibility is this may not be a uniform conduit. Rather, if it is also the conduit which is having some uniformity but in reduction, then also that mass flow rate will follow the center line. So that means if I take any reference from the center line, the height would be same. So if it is a uniform shape, that mass flow rate will not deviate, because this will follow the same center line path of the actual body, because this will be uniform. But if it is not uniform, then your thing will be different. So you can say that this is horizontal, this is something like that, but this end there is a height. So in this case, this will not follow the center line. So then it may happen that it is following this path. So then height will be different. So this is a complex one. So in that case, we have to find the center of mass here at this point, center of mass here. Then we can, if we join, we will get the exact height of this. So this is a differential, that complications I will not go into. So this will not be very much there in lower study up to that 12th standard. This much complication is not there. So we will stick in the regular figure and uniform figure, where we can assume that mass flow rate is moving to the center of the body. So their height will be uniform. So these are the two conditions where if it is rest and if it is flowing through a horizontal of equal height conduit. Okay. So there I'll end my this session. In the next session, I'll move on to more theories, and intermittently I will also solve some problems to understand these theories better. So thank you for now.